Cool. Thank you. My name is not Jordan Sosnowski. My name's
Could have fooled
Charlie.
me.
So what?
Could have fooled me.
Oh, hey, don't say that. Let me figure out how to do this. All right, so we're gonna be going over advanced static analysis. So before we get started, who is familiar with C, like the C programming language? Who has coded in C? Okay, so we got a little bit here and there. Maybe like, have you not? Like back there, far corner? Yeah. Okay, that's okay. It's not. Have you done Java? What about you, Ismail? Have you done any C, Java?
I mean, I've done like a few things in C. Okay,
Okay.
pointers count? If I don't
Yeah, pointers is fine. I mean, like, it's okay. If you've done, like, a compiled language, you should be okay. Who has dabbled with assembly? Okay, that's good. Because that means we get to skip a lot of the fundamental stuff and get into some of the nitty-gritty stuff. We'll zoom through it. But I want to go through it really quickly so you can kind of refresh on it, and then we can start like messing around with something called godbolt. It sounds cooler than it is. I mean, it's pretty cool, but basically you take C, and it'll spit out the assembly, right? So you can kind of go in and look at like, hey, what's this construct doing? And then after we've done that, we can start looking at malware and kind of going through that with something called IDA or IDA free, I think is what they're referring to it as. But that's what we're going to do today. If you want and you don't like IDA, you can work with Ghidra. Or if you've never heard of any of this, don't worry about it. Before we get started, does everyone have a VM or a computer that can or has VMs on it so you can kind of look at malware and look at all this stuff?
I'm trying to get one set up. I just got this.
Okay.
Okay. Yeah, I was gonna say it's at the link in the announcement, the
Okay.
RE VM or whatever. Oh, and also, if you can't get that set up, we have Mac links up here. With VM.
Yeah, I've never installed VM on Mac, so I'm trying to get that working.
Okay. So
I can do one Mac or on
Oh.
don't use that.
That
Yeah.
doesn't work.
I'll just borrow one.
Yeah.
Yeah. So if you guys would help him get started with that, just so we're all on the same page, because you're gonna want that. I promise you.
You want one or two?
Two. Okay. Cool. So because we're all pretty familiar, I'm gonna speed through a lot of this, but
Sucks. You can turn the scale.
So what is binary reverse engineering? Is anyone familiar with reverse engineering? What is reverse engineering?
No, it's looking at what something does or looking at like the output of something and figuring out what it does.
Sure. Yeah. So like, in some cases, like when we're talking about binary reverse engineering, we're talking about one of two things: software reverse engineering, where you're given like the source code, and then you have binary reverse engineering, where you have like an executable or an ELF file, and you're going in and you're trying to figure out what it does using several different techniques. Last week, we used basic static and basic. We didn't do basic dynamic, did we?
You did.
We did? Okay, so we did those two things, but now we're going to start diving into exactly what a binary does as opposed to kind of guessing what it does based off of what we see with the output. So that's what we're doing today. Don't really need to worry about soft skills, but yeah, it can get a little frustrating. It can be hard. Don't give up. Google everything if you're not familiar with it. Start learning. There's going to be function and API calls that you're not familiar with it to start with. Heck, today we were looking up API calls within like the software reverse engineering course. So, I mean, you're going to run into things you don't know. It's okay to Google them. And in fact, you should Google them so you get a better understanding. So it's used in a couple different places. a few of us have done an event that's coming up last year. It's called the Cyber Boot Camp Tracer Fire. Sandia National Lab hosts it, or well, we host it and we help with that, kind of. So that's coming up. By the way, check out the Discord. That's coming up January, and the registration opened. That focuses on incident response. So reverse engineering, malware analysis, kind of plays into one of the pillars of incident response. Other places you might use it is binary exploitation. I'm sure like 90% of you, well, maybe like 80% of you are in Dr. Springall's course, so you're pretty familiar with binary exploitation. But we're not doing that right now. Right, so we talked about that a little bit. So is everyone familiar with like number systems? So like decimal, binary, hexadecimal, octal, that kind of crap. Does everyone know how to convert it? Okay, then I won't bore you. If you're all familiar with it, you're gonna get pretty used to seeing hex. Well, I'll put it that way. So if you're not comfortable with it, that's okay. Just practice on your own time. It's just something you get used to. Same with binary. Is everyone familiar with Indianness? Okay, cool. Data sizes, you're probably going to see words, bytes, double words. I can't say I've seen too many quadruple words within that, but I guess I don't always pay attention to the nitty-gritty parts. One thing to note, just as an aside on that, when we're going through this, do not get lost in the sauce. So, like, basically, we're going to be looking at assembly, and we're going to be looking at a lot of assembly. So if you get fixated on looking at a single line and understanding it line by line, you are going to get so lost, because it's really not that important that you understand every single line. You will, but looking at it from a higher point of view, a higher level, is much, much easier to understand and conceptualize what's actually going on within malware. So just as an aside, and keep that in mind as we go. So here's what is assembly. So it's basically a mapping of machine code or opcode to some mnemonics within like a computer. So like what your computer understands from machine code is translated over to assembly, which is much, much easier to work with, believe it or not, for us. So in this instance, we see a NOP translates to 90. We're going to primarily focus on x86 assembly. You can do x64 assembly. It's a little more complicated, but it's about the same. Let's see, there's different registers and different information that goes with it. If you need me to slow down, let me know. I'm speeding through the slides, so just raise your hand and I'll slow down. This is what is this? Yeah, the von Neumann architecture. If you've taken architecture, computer architecture, or I think even in Java 1 and 2, Dr. Hendricks mentions the von Neumann architecture. It kind of comes into play here, but that's all fundamental information. Registers. What's a register? Anyone?
Isn't that like what you have at a wedding, for people to buy stuff?
Yeah, that is a register. Or no, that's a registry, right? Something you put money in. Okay. You take money from it? Okay. Okay, so it's like this. It's a really small unit to store things. Sort of like your cash register, only for bytes, right? So, yeah, we have 8 general purpose registers that we're going to deal with. You've got EAX, EBX, ECX, EDX, blah, blah, blah. Your E flags. Because you all know all about assembly, you're experts in assembly, I'm going to gloss over a lot of this. As we're going through, if you run into issues, I'm going to post these slides so you can refer back to it. But and you can thank Jordan for that, because he worked his butt off on these slides. I can tell you right now. But yeah, EAX is this, what is it, 32-bit register. It can get split up, so you can split it into AX and AH and AL. We'll probably see more of AL and EAX when you're working with malware. So like bytes and then like a 32-bit for addresses. So flags, the ones you really need to worry about are the 0 flag, the carry flag, and the set flag, right? Yeah, set flag. You all are familiar with those flags, right? Everyone's shaking their heads. Cool. What about on Discord? Are we getting anything there? Is there anyone in there?
Somebody watching.
Okay, what about YouTube? Okay, we're at a nice
I
point.
think the
Okay.
only person might be me. I have the screen pulled up, so.
Probably. All right, so memory. It's there, right? So we've got main memory. It's composed of the stack, the heap, code, and data sections, right? So each one of these plays a different role within your program. Code, can you guess what goes in there? No, okay. What about data? Is anyone familiar with what's in the data section? Maybe if you're talking about segments, our data. What's in our data? Strings and stuff like that. So it's things you don't really change. Stack's going to be really important. You're going to want to know what stack is. At least with what we're doing, that's where you're going to be pushing in arguments onto the stack. You're also going to be allocating space on the stack for your local variables, for your functions. It's going to play a big role in the next few slides as well. So here on the right, you can kind of see our main memory, but you can also see a couple different registers, right? So can anyone tell me what 2 registers are associated with managing the stack?
EBP and ESP.
Yeah, all right. What's EBP for?
Base pointer.
Base pointer.
Base pointer.
Okay, what if we're talking about a stack frame, what is the base pointer for?
Top of this, not top. Well, if you're looking at that.
So,
Oh, yeah. it
yeah,
is.
so it's the base of the stack frame. So it
Yeah,
points,
bottom.
it's like the beginning of your stack frame, right? So you use that as a stable point to refer back to the parameters as well as the local variables. Because if you use the stack pointer, what's going to happen? What is the stack pointer responsible for within the stack?
It points to the top of the stack.
Points to the top of the stack, but it's constantly moving, right?
Yes.
So if you were to use that for local variables, what might happen?
Well, you could lose them, or you have to constantly keep track of how much you're moving ESP
Yep.
and where the variables relate
Exactly.
to that. And just use EBP. It's easy.
Yeah, so for those, I don't know if you can hear it in the recording or the stream or whatever, but what John said was, the stack is going to be constantly moving, and you don't want to, if you're referring to variables or parameters, you don't want to have to refer back to or keep track of what the stack's value is, so you can actually find what you're looking for. That's where the EBP where it comes into play. Who that? Hey, Drew. So which way does the stack grow? Down. Okay, cool. So I'm harping on the stack a lot because it's where a lot of confusion comes into play. So yeah, okay. This is kind of how the stack works. So you can see right here our EBP points to 29, ESP is pointing to 44. When we push 10 onto that, you can see it's OA. What's that in hex? Or what is that in decimal? OA. 10. Sweet. Okay, cool. Push 40. What's 28?
40.
Yeah, good job, John. We pop EBP, so we're popping that into what? Doesn't matter. And then we push EBP. Or yeah. So here we've got some C code, and all right. here's a little bit of trivia, right? So with the current architecture we're using, our current standard, I forget the terminology, but say what? Convention, yeah, calling convention. If we get to a function call, which of those two parameters is going to be pushed to the stack first?
Which convention are we?
C-decal.
Oh, isn't that right to left?
Right to left,
Yeah.
right, that is. All right, so we can see we push 4, we push 2, and then we push the return address. Why do we need the return address? Cool. Okay, and then you save EBP of what? The previous function, correct. Why? Oh yeah, so we can get back to the function call basically. And then we push C, so that you can see is the first variable within that. And EBP minus 4, right? Because how many bytes is an integer within a 32-bit architecture? I don't know if that really matters. Within C. 4 bytes, right. That's why it's EBP minus 4, right? But yeah, so we're going to, okay. We won't do the quiz. We'll get to some fun stuff. Don't need to know that. What's the difference between Intel and AT&T? This is like an OS, or what is it? Assembly class? What?
I said one cell cell phone.
Yeah. Well,
Actually, probably both.
both of them probably at this point. But so you're gonna see it here, right? So within like the instructions. So on Intel, which side of this is the destination and which side is the source? Right. So it's kind of like what you see in like programming languages. You can kind of think of it in that way. So like EAX in this case would be like your variable, and your equals is equal 5, right? So EAX equals 5, right? You're moving that into there. Versus AT&T, which is flipped, right? And people get a little confused, but there's also other characters in that. So
Also has, it's more like explicit to generally like instead of just adding an inferred size of 4 bytes to ESP based on the destination, it adds like, or it explicitly specifies the like add a long 32-bit value to this destination register.
So yeah, you are typically more explicit within AT&T. But we're going to be focusing mostly on Intel for this. So don't worry too much about that. Common instructions. We're going to zoom through these, assuming you all know them. So move. What does it do? It moves. So you're moving data from the source into the destination, and that can be, you can kind of think of it as like an equal sign within like a programming language, right? So you can have like a value that you're pushing into EAX or register, and I think you can do addresses as well if I remember correctly. So yeah, you can dereference things with EAX using square brackets right there. So on the third line of the code, you can see EAX contains FF40. In this case, we're saying that that's an address, and the value of OX20 is inside of that address, so we can dereference the value that's inside of EAX and then push that over to EBX. That's kind of what that's doing. Is everyone comfortable with this so far? Is anyone confused? It's okay if you are. Okay, I'm going to keep zooming. All right, so load effective address, LEA. What does that do? It's a lot like move, right? Yeah, so instead of like dereferencing in that case, we're actually going to take the value that's in EAX and push it over to EBX. So it's about the same. Again, we will have this available so you can refer back to the functions if you get confused.
It's a classic example of like x86 being just having too many ways to do one thing. Like LEA is literally just there to make pointers easy and stuff. And
It's really nice for like jump tables,
yeah,
but
you can
like
do
but
arithmetic like that. But at the end of the day, should there be an instruction that
it works. It's there. So yeah, you can see here within the arithmetic, or you do quick arithmetic within LEA, so it speeds up. Like the real reason it's there is to speed things up, to optimize things. So like in this case, we go ahead and do the computation inside of that, and then we directly push it instead of like loading EAX with 20, then multiplying by 4, or I guess plus 8, so shifting right 2 or 3. So yeah, it speeds things up, and that's generally where you see it. So like one of these would have like an offset for that kind of thing. Add, what does it do?
That's addition.
All right, it does addition. I think that's enough said about that. Subtract, what does that do? Subtraction. Increment and decrement.
It increments and
By one.
Man, you guys are sharp. Shift right, shift left. What do they do?
shifts right, shifts left.
All right, so in effect, what is this doing though? Like if I were to have a value within EAX and I shifted right, what would that do?
Make it smaller.
Make it smaller?
Wait, no. Sorry.
Yeah, you're right. Yeah, so by what though? Yeah, correct. Yeah, so we also have shift logical left versus shift arithmetic left. I would just look up the differences. They're pretty similar.
Isn't the main difference just one shifts zeros in and the other shifts ones in?
Yeah, it keeps what
It's like
If I remember right, one of them adds a zero on the side that you're shifting from. The other one, if I remember right, rotates. So
I think that's rotate. Like there's a
wait.
there's a
Oh.
ROR or an ROL or something like that. So, yeah, another instance where it's kind of something like that.
it's
But
not as simple as
yeah, so don't worry too much about that. You will see shift left and shift rights for some like basic crack me's and things like that, but we're not doing that today. So we can come back to that when the problem arises. But just know it's shifting. Usually shift left is like multiple of 2, right? You multiply whatever's in there by 2. Shift right, divide by 2. Yeah, SAR and SAR, so yeah. Same difference, other direction. Mul and imul, what do they do?
They multiply.
Multiply? What's imul? Why is it different? Why do we need another one?
Well, it's signed.
One signed. Okay, cool. Which one's signed?
The imul.
Imul. Cool. Div, idiv. Divide. Cool. All right. Size directives. I don't think that's really necessary for this right now, so we're gonna skip that. Logical. Okay. Has everyone taken digital logic circuits?
you're right. Now let's rotate. Arithmetic shift leaves whatever bit it is.
Yeah.
Oh, yeah.
In a sense, it's odd bit, depending on which direction.
Yeah.
It's whatever because when you shift, you now have a hole.
Yeah.
It's whatever it fills there. Rotate takes the one that fell off, puts it there.
Yeah.
Arithmetic keeps whatever bit there and shifts.
Yeah. So it keeps signed basically. Okay, has everyone taken DLC or like a basic logic course? Yes? No? Maybe? Okay. Ands, ors, we're going to see a lot of XORs, and we'll see why those are important later. Not so much. Yeah, they do the same thing within assembly. So if you're familiar with that, it's bitwise operations though, so you've got to kind of keep that in mind as you're going through. But it does the same thing. XOR, is everyone familiar with an XOR? Yes? Anyone not familiar? It's okay if you aren't. It's not like the most common logic gate. Anyone? Trip?
Truth table.
I'll give you a truth table. Okay, we'll go back to the truth table. Okay, so 1 XOR 1 goes to 0, right? It's an exclusive OR. So 1 XOR 0, 1. So as long as you have 1 and a 0, it'll go to 1. If you have a 1 and a 1, it goes to 0. 0, 0, 0. That's XOR. There are some interesting properties that go with that, and if you went to the crypto course, or not crypto course, if you went to the lecture, I think that's on the YouTube channel, you'll see why. We'll see that applied here, probably.
Should I go? Well.
What's up?
I was going to add, like, in programs, you do see that very commonly. XORs are used to clear registers.
Oh, yeah. I think.
You may or may not.
Here it is.
But, like,
Yeah.
Yeah, usually in programs, a lot
Actually,
of
no,
times
it's
you
not
will
here.
see, like, XOR EAX, EAX. And
Yeah.
then zero out.
Oh, dang it. Okay, I was going to ask them. Okay, so yeah,
Oh.
XOR EAX,
Okay,
EX. You're XORing it by itself, right?
Yeah.
So it's always going to be 0.
Everything's
so
going to be the same, so it's all going to zero.
it's just a really fast way of zeroing something out.
So you'll see
Nice.
that very often.
There's 2's complements. I think you all know how those work. Everyone familiar with 2's complement?
I'm tired of doing this.
You're not familiar with it?
Totally forgot.
Oh, too bad.
Look it up.
Yes, it's
Yeah, flip the bits and add one.
yeah. You flip the bits and add one.
Makes unsigned to signed.
Yeah, it's a quick and easy. Labels. What do labels do in assembly? Why are they important?
Label location.
It does label a location. Good job. All right.
Access
Why do we use labels?
to jump to a location.
Readability.
Yeah.
Exactly.
Readability.
I've
That's
never commented before. I don't know what this is.
compares. We're gonna see a lot of those.
Well, I was gonna say labels are Wait, were you gonna?
No, go ahead, John.
Okay.
Go ahead.
Well, I was just gonna say labels are essentially like just a more like usually they're automatically generated. Like it's not like a comment or something. They're almost always used for like very commonly for like function names, and they're usually generated because it's way easier to say refer to like main instead of like 0x00401800.
So in an actual binary, if we're reversing a binary, are we gonna see labels?
I mean, I think IDA does auto label main, but other than that, no. But you can rename stuff, like if you figure out what something does.
So you're gonna see memory addresses, right?
Yeah, it'll just
So-
show raw addresses.
Because these are when you compile. This is easier for you. It's like I said, assembly, believe it or not, is actually easier to work with, and they do things like this, which are for convenience. So convenience and ease of reading. So labels, you're not going to see these in what we're doing. Item might, like John said, add something that looks kind of like a label, but you're usually going to see something like a jump to a sub directory or not subdirectory, sub function. I can't think of the word. Subroutine. Yeah, subroutine. So we'll see that later. But yeah, what is this? Compare. Where do we use compares and why are they important? What was that?
Numbers.
Numbers.
Numbers. Yeah. So like it's kind of like yeah, you're subtracting the source from the destination. So on the left, like common Intel structure, we have destination on the left, source. So you subtract the source from the destination, and then you you don't really do anything with the compare. It's not until you get to a jump or you use that whatever value that you get from that. That's when you see it. But we're usually going to be using which register after compare. Register. E flags, right? So we're going to be using a bit within the E flags register. So like a 0 flag or a set flag or something along those lines. So here's kind of like a table with a carry flag or zero, not set flags, excuse me, carry flag or zero flag with each one of the kind of parameters. Say what?
Or the overflow flag.
Not for this one, I don't think.
I think it may set the overflow flag, but I don't think that's typically used in like programs.
No, I would not put it past Intel to have a jump statement for carry flags, but
With the E-flags do a whole lot of really, really complicated stuff.
Mhm.
It's best just to ignore them unless you really need to.
Yeah.
Usually a compare is immediately followed by a jump, not equal.
Yeah.
Right.
It's straightforward.
yeah, you once you see it, you'll know, hey, this is subtracting and we're jumping to one location, or we're doing something else, right? So test, this does what in comparison to compare? Like, what's the difference between these? It ands it, right? So yeah, testing EAX against EAX, what's that going to do? What is that doing? What's that doing? Test EAX to EAX. What in effect does that do, I should say?
Flags.
Hmm?
Flags.
It would be checking kind of the value of EAX, right? So it's anding EAX against EAX. You commonly see this to check if EAX is 0, right? So that's what that's used for commonly. So you're checking 0 flag right there. Otherwise, it's a 1, or well, it's not 0 in that case. So you'll see that in like immediately after return calls to check for like
I don't know,
exiting.
there's something to add.
Yeah,
Why
what's
would
up?
why would we use compare we use compare and test for like conditionals for like jumps and stuff? Why would we use like compare and test versus just say sub or and? What would be the advantage of using those? Why not just use like and instead?
Because it doesn't store would be one thing.
Yep, exactly.
Non-destructive.
Good job, Vicky. Non-destructive. It doesn't
Learned
actually.
that today in class.
Nice. It doesn't. Yeah. Both test and compare don't actually modify anything in the registers. It just sets flags. So yeah, that's the main advantage of those. You can check values without actually modifying the values.
All right, so yes, that is true. So that's one reason why we use compare and test. They're non-destructive, which means they're not going to change the state of the program. They're not going to change the state of the registers. They're just going to affect like where you jump or not jump, rather. So speaking of which, we've got jumps. So we have got conditional and unconditional jumps. Unconditional jumps are just going to jump no matter what. So there's a little example with like actual assembly right there. So you see jumps to add after main, and that goes through and it jumps to L3, I guess. Oh, it jumps 13. Okay, but anyway, you know what jumps are. Conditional jumps, there are tons and tons and tons of these. It's okay if you don't memorize all of them. Most of them you can kind of figure out by the letters that are contained in them. JZ jumps if 0, if the 0 flag is set. Jump not 0 jumps if the 0 flag is not set. So you can kind of figure them out by what they are. Jump less, jump greater, so on and so forth. We won't do that. Call and returns. So what is the call used for? You can refer to the slide if you want. It's used for calling subroutines, right? So you jump to not jump, but you go to a certain address and you do the subroutine there. Yeah, so there's some background that goes with that. You mess around with instruction pointers mostly, as well as return, which is kind of the opposite of the call in a way. Conditions. Yeah, so right now we're going to go to godbolt, and we're actually going to do this ourselves. So this one you don't need a VM for. Go to, come back to this. Godbolt.org, and you'll come to this page right here. So what we're going to do is we're going to oops. So what this site does, I mentioned it at the beginning of this, you can pass it C, or I think maybe other languages. I've never actually played with that. Yeah, you can do Ada. Gross. Okay, yeah. So you can mess around with C. We're going to be working with C for this, and you can immediately see the assembly on the right. Yeah. So play around with it for a second. Make a program really quick. Don't make it super complicated, and then talk to your neighbor about it, or talk to someone in front of you and to the left, or in front of you to the right. Talk to someone you don't know, and just, in fact, no. Is everyone on Discord? Okay, how do we share the code and try to figure it out really quick? We're going to have them figure out what the code is doing. So if you're not on the Discord, get on the Discord real quick. Make your program, take a screenshot of it, and then have someone pick an assembly that's not theirs and try to figure out what it does. Reverse engineering. Put it in that channel. Sure. That works. Doesn't really matter. You can do general.
Same place that I posted the godbolt.
Yeah, so if you didn't hear Ethan, what we're doing is we're taking a screenshot after we've made the program of the assembly, not the C, and we're posting it to, you said malware analysis? Malware analysis channel within the Discord.
Post it like verbatim in like a code block or something.
You could do code block, you could take a screenshot, whatever is more convenient for you. And then after you posted, pick someone else's, try to figure it out, and then we're going to spend, well, you're not too comfortable with C. I don't know, 10 minutes? Does that seem fair? It doesn't have to be complicated. We can tone it back.
C++ as well.
You could do C++ too.
I mean, yeah, it doesn't.
Yeah, I mean, as far as those like basic data structures, isn't it essentially?
Yeah, just make a basic thing.
What's the thing for getting rid of optimization?
I don't remember. There's a
Capital O.
No, capital O gives optimization.
That sets like the optimization
Well,
with zero.
Okay. Can everyone see the flag I just added?
One is
yeah, so attack O zero should say.
one is code size.
All right, so those are your flags right here. So the N32, as far as I know, is saying, hey, use 32-bit. The TAC O, like Tripp had said, is toggling. It's the optimization flag. So we're doing a 0 to say, hey, don't optimize this. Which, if you're not familiar with compilers, they're going to try to optimize the crap out of your code, which is going to modify the assembly. We don't want that. We want it no optimizations because, well, in reality, most of the code is going to be optimized. But for this exercise or this thing, we want to actually see what's going on without tamper. So, yeah. just as a little bit of inspiration. Here's some C code. Just, oh, that's tiny and hard to read. There you go. Was everyone able to find the website and everyone on the Discord so you can post your code? Don't be embarrassed by the code. Did anyone else see that Emotet's live again?
What's live?
Emotet. It's kind of bad.
That's
Yeah,
what
I know.
I'm thinking.
Okay,
Brendan
alright.
Fraser. Okay, I'm just thinking we need to call Brendan. Look, he's making a comeback right now.
Did you see the last one? It wasn't that good.
I did. I saw it for the first time this year, and I kind of wish I did.
You're not talking about the Tom Cruise, are you?
Yes,
They made a remake.
What's happening?
the
Or
one.
they made a reboot.
Oh no, they made a Brendan Fraser one.
Wait, really?
Years ago, after the Tom Cruise.
Really?
Ooh. I did not know that. That sounds.
And I'm in some like mummy meme groups on Facebook too, like specifically for the movie.
Oh,
So I'm just like,
Really? There's only one outlet here?
You can upload that
All right, how's everyone doing? Everyone get their program? Everyone ready to reveal? I'll take the silence as a no. Dr. Springall, did you make your C2 yet? Over there? You making a C2? C2? Oh, okay. Fair enough.
where are we putting it?
We are either posting the code or taking a screenshot and putting it in. Ethan, you said malware analysis? Yeah, the malware analysis channel.
Okay, looks like mine's the only one there.
Oh, you went x64. Can you add a TAC M32 on your compilers? So, like up here, can you add this flag? And also this flag as well. So just both of those. Okay.
I didn't like that.
So just the assembly you said?
Yeah, just the assembly.
with labels?
Sure.
Oh boy.
Can you add the M32 on that as well? I don't really want to debug or go through a 64. Oh, Vicky, I think that's the same one.
Oh, yeah. Oh wait, I don't know if I'm talking to delete messages. What is this? Oh.
There we go. Nice, Vicky.
Oh,
I barely did anything.
what did you do?
I put the things he told me to put on there.
All right.
Yeah.
Well, let's take a look. I'm kind of afraid to look. Has everyone got their program up? Trip?
Along the Discord with Dr. Ross
Let's
in it.
hide that. I think that's Tyler's server.
Wait, which one's Tyler's server?
Dr. Cross one.
Oh, yeah, that is not true.
Where is it? Oh, I'm in it. That's why. Wow, I'm blind.
Also, I'm in one with, VS. That's the CSS.
All right. So, all right. Has everyone posted? Everyone who's planning on posted? Okay, cool. All right. Zach, would you like Tom S's? Hey Tom, could you add the M32?
What I gotta do?
So you would add this flag right here. Yeah. So right now, no, you're fine. Just makes it so they're using the registers we've been talking about.
In the capital O0.
There we go.
All right. So we'll start with Ismail's because it looks easy. All right. So can everyone see that? Is that visible? All right. So what is this doing? I think it starts at L2.
So he's calling his function,
Yep.
and he's doing a shift arithmetic left on whatever is in EBP plus 8. And he's comparing that to 2.
Okay. It does not start at L2, by the way. Now that I'm looking at it. Shifts
Yeah, you're right.
arithmetic left. Yeah. Compare to 10.
So it's a recursive.
Compares to 10. What is JLE? Less than or equal? Okay, so if it's less than or equal to, and that's EBP plus 8, right? Whatever that value is. If it's less than or equal to 10, where does it jump? Okay, what is L2? Like, what is the name for that? A label, right? So we're jumping to that memory address, right? And what do we do at L2? Okay, yeah, it is recursive, you're right. So yeah, it looks like, what is the ESP minus 12 for? Add 16, call function, add 16. All right, Ismail, what does this do?
I mean, it's just a recursive function that adds like I to I, and then if it's greater than 10, then, oh snap, I actually made this an infinite recursive loop.
Yeah.
It was supposed to be less than, and I'm like, why is it?
Less than or equal?
Wait, no, I think it's fine. Yeah,
I think it's okay.
Recursively loops until it adds up to more than 10.
Man, you guys went hard on these recursive functions. Goodness gracious. All right. That's too long. I'm sorry, Tom.
I know, man. I just figured I'd throw it in there and see what happens.
All right. So what is this doing? So we push EBP. What is this? Zach, do you remember the name of the additional call, or the top of the calls? I forget the name of it. The term. What?
Prelude.
Yeah, the prelude. So the first 3 calls, are they super important? What are they? Actually, the first 2 calls, we don't. Yeah, that's hard to see, man. There we go. We're setting stuff up with that, right? The sub ESP, we're allocating stuff for the stack, right? We're allocating space. What about line 5? What are we doing there? We're doing an assignment, right? For okay. What are we?
Wait, it's prologue and epilogue. That's,
Prologue and epilogue. Yeah, sorry, not. We said prelude, right?
yeah, it's like they like count.
Okay, yeah. So it comes at the beginning and the end, right? So the line 5, we're assigning something to EBP minus 4. Do you remember why we're using EBP?
That's the bottom, I guess the top or bottom, depending on which way you look at it, of the function.
Sure, it's pretty stable, right? The base, yeah. Line 7 or line 6 and 7 doing the same thing, right? We're doing assignments. Let's see, EBP minus. What is line 10 doing, and what does it affect? All right, what are the values in EAX and EDX? Yep, 7 and 3, right. And then what's line 11 and 12 doing?
That's we're adding EX to EAX. EAX to
10 plus 2. Yep, that's right. So we're taking whatever's in EBP minus 12. You said it was 2, right? And we're adding it to EAX, which we just found before, right? It was 7 plus 3. So we're getting 12. And then what are we doing with that value?
We're moving it to EBP minus 16.
Okay, cool.
And then you're moving it back into EAX.
Yeah, so that's where you would see like the optimization would kind of get rid of some of that, but yeah, that's just compiler nonsense, really. So EAX would store that into like the stack, and then like typically you're going to return EAX, so we're pushing that back from the value that would have been, or a variable in this case, and pushing it into EAX. But yeah, so with that, I guess that's not super duper interesting. I would like to. Oh goodness. Okay, I'm afraid to look at trips, but is it not bad?
Well, it certainly came out worse than it should have.
Okay, so we'll leave these in here. I encourage you all to go and look at them and then like talk to whoever posted them. But we're gonna go into now that we've kind of seen what happens when we actually compile and what's produced from that. We're gonna go and look at malware at this point. So before I do that, let me just verify there's nothing crazy in here that we're missing. So we've got conditions, talked about that, loops. Okay, so these are kind of C constructs and what they look like within assembly. So conditions, you've got your jump statements and your labels in this case, and you've got compares, right? So in this case, we would be, oh, let me go to presentation mode. In this case, you know, what's being compared right here, and what is it being compared to as well? I and 10, right? So in this, we move EBP minus 4. What do you think EBP minus 4 represents within the original source code? I, right? What about EBP minus? Oh, excuse me. Yeah. Yeah, you guys are spot on. So yeah, that comparison. Why is it 9 instead of 10? Yes. Well, no, it's because it's less than 10, right? And then it's jumping if it's greater than. I mean, yeah, we'll get used to that. So loops, they look kind of similar, except they're going to loop back. Well, it's really clear when we go to IDA when you see a loop. But yeah, so here we can see, and we saw this in Ismail's as well. We saw a loop in the assembly where basically you go through and, well, yeah, it's a loop. Trust me. We'll see it when it gets to IDA. Arrays, you can see we saw this something similar with Vicky's, except those were variables in that case. But you allocate this big chunk of memory on the stack, and then you start pushing values. Why do we start with EBP minus 24 as opposed to EBP minus 12? So it's the bottom. Okay. Why do we start with the bottom?
Stack.
Isn't this scenario where it'd be like a convention, right? Maybe. Right here. Arrays, where we push onto the stack. Or not push onto the stack, rather. We put it into local variables. Anyway, just keep that in mind as you're going through. It's not super important, but something to note. Characters, functions, we saw that with our own code, right? Through here. Decompilation versus disassembly. One tool, Ghidra, has a decompiler built into it. It's free. We're not going to be screwing around with that too much. IDA, no Ghidra. But we will be messing around with a disassembler. So that's going from assembly code back to, well, excuse me, going from a binary back to assembly code. So we're going to be getting, this is why we're covering assembly, basically. Decompilation, compilation, I don't know what I was about to say there. That would go back to the source code, right? So it can only go so far. It's not perfect. That's a very complicated process. I actually have no experience with that. So I know it's very hard, though. So Ghidra has that. IDA Pro has that, but that's like thousands of dollars, tens of thousands of dollars. So fortunately, we don't have that luxury right now. But I'm familiar with IDA, so that's why I'm using it. But again, if you're familiar, if you want to use Ghidra, by all means, go for it.
If you don't already know IDA, go with Keeper.
Yeah,
Trust me, it's gotten just as good as IDA.
yeah, he is right though. Ghidra has a lot of the. Ghidra's pretty good. It wasn't always good, but it's gotten a lot better. So when we're looking at malware, last week we talked about the top two, basic static and basic dynamic, right? So when we do basic static, just as a refresher, we're looking for strings. We're looking at what's imported, what's exported. We're looking for specific values within the binary. We're looking at resources that are inside of the binary. Basic dynamic, we're looking at the behavior of the binary while actually running it, which is another reason why we want these VMs. We want these VMs even if we're doing static analysis. You don't really need it, but I digress. We just talked about advanced static analysis, and we actually, believe it or not, did some when we were working through godbolt and some of the assembly. So you're now reverse engineers. But yeah, we're disassembling it, and we're reviewing the code, and we're trying to logically piece what it's doing, and actually, well, we're piecing together what it's actually doing. The last step we might get to, I doubt it at this point, is advanced dynamic analysis, and that's taking a debugger, so something like x64dbg, IDA to a point, or Ollie debug as well, but we'll get to that when we get to it. We might not get to that this semester, but maybe next semester. But yeah, so you kind of want to go, in general, you kind of want to go down from static all the way to dynamic in that order. I really am not too fond of basic dynamic analysis because I think it takes too much time, and I'd rather just debug it and look at it IDA. But I don't do this professionally. So anyway, so like I mentioned before, and we covered last week. Yeah, what's up?
I was just gonna say, kind of that graph. You can almost kind of view it as like a funnel in a sense that like you start with the super broad view basic static, and like that gives you an idea of kind of what to look for advanced static, and then if there's stuff you can't figure out in advanced static, then you'll kind of be like, okay, I want to look here, here, and here with advanced dynamic to see what values are here, like you can't figure it out. So
yeah,
like that's kind of why too, like it's usually you're kind of narrowing your scope each time, going from like, okay, I may want to see if these functions are actually here, or like what's getting passed to these functions, to like, okay, I have these functions and I know what's being passed here, here, and here, but I don't know what this one value is, so I need to actually run it and run through it step by step to see like what is it. So yeah, right.
Yeah, John's absolutely correct. By following this, you increase the speed at which you can understand the binary. So, like you said, you're getting information from static analysis, so your job in basic dynamic is a lot easier and a lot quicker, and so you get a better understanding quicker. Advanced static analysis is a slow process, but yeah, we're taking information that we see in the previous steps to make our jobs easier in the latter steps. Generally, with advanced static and dynamic analysis, we can do those in pairs. So we can go through and, like, if we find something we don't understand is way too complicated for us to kind of work through in a reasonable amount of time, we can just set a breakpoint in the debugger, jump to that point, and look at what it does in reality. So that's, you get a process as you go through this. Basic static, we covered this before, but CFF Explorer is kind of like PE view. We're looking at imports. We're looking at the PE values. We're pulling stuff like that. Strings, we're looking for hard-coded values within it, maybe like URLs or even functions. Well, definitely functions. PEID, we're looking for packed binaries. But we can go into that in more detail at another time. Basic dynamic, Procmon, Proc Explorer, RegShot, Wireshark, Netcat if you really care, INetSim. There's just tons of tools. Generally, you want like stuff for registry. You want stuff to look for, Windows calls and events. So Procmon, Process Explorer gives you an idea of like what's in memory, what's the process doing. Wireshark, you can look at network traffic, but you kind of you pick the tools that work, and from static analysis, you kind of get an idea of what you need based off of the imports, unless it's packed. But anyway, that's there. And then for what we talked about today, IDA, Ghidra, Radari 2, I think that's how you pronounce it, Binary Ninja. They all do pretty much the same thing, but they do it in different ways and have their perks depending on which ones you use. Some are better at some things than others. Industry standard right now, although they're kind of moving toward it, moving toward Ghidra, is IDA Pro. Like most professional reverse engineers use IDA Pro, but it's really expensive. So we're using IDA Free or Ghidra. And here's all their things. Thanks, Jordan. X64 and X32 DBG are what I use for advanced dynamic. WinDBG, as far as isn't that for kernel debugging?
I think so.
Yeah. We are not touching that right now. OllyDBG, just use X32 or X64. It's newer. Ollie is kind of gross, in my opinion. Immunity, I've never used, so can't really speak from that. There are VMs that have all of these tools for you. I think, in fact, some of the laptops we've handed out have all these tools, or at least the ones that some of us are familiar with. So this was at a point possible, but we no longer have that server running. And now we did the godbolt. All right, I'm going to rely on John and Zach to tell me which lab we're going to be working on. So we're going to be doing malware analysis now.
So Ghidra does have a debugger.
Yes, yes it does. I prefer like standalone debuggers personally. IDA's debuggers kind of, it's okay. It's not great, but
Ghidra's is supposed to actually work.
So this is IDA. It's a really, really old version. So the ones on the Macs probably look a little better.
No, that's
Is it?
Yeah, it's XP. It's
Oh, never mind. You guys get to work with old IDA.
That's like the only one that's like publicly available.
All right, so I've got a little, way too many things on my desktop. You probably don't have any, I would imagine.
Well, you should have most of the tools and stuff. Like
Oh, they're on the desktop? You got shortcuts on them? Okay, so is everyone running a VM? Does everyone have this cool Windows XP background in front of them? Yeah? Okay, cool. So there should be a folder called Practical Malware Analysis Labs. So this is kind of the go-to malware analysis and reverse engineering textbook, I guess you would call it. If you're really into this stuff, I would highly recommend buying this. You're going to learn a lot from it. But which lab are we doing?
Those from 6 are not too bad.
Okay.
All these are still a little bit.
We can either jump into the fire, or we can go a little easy. It's up to you guys. Actually, jumping into the fire would be pulling like something off the internet. But we're not gonna do that today. I tried convincing them like we should go look at Emotet and TrickBot, but they were like, nah, we're not doing that.
Yeah, because I don't want to be the one facilitating passing out real malware. That's why I said don't do that.
It's safe. We're in a VM.
Well, you have to pass it to get to the VM.
That's true. So, John, what are we doing?
I'm looking at them to see like which one is probably the best.
Okay.
I
Ethan?
think 6.2 is a decent amount of. I don't know. It has a decent amount of stuff going on, but I don't think it's incredibly complicated.
Okay. We'll do.
It builds on itself anyway.
Yeah, it does kind of.
It gets more
Yeah.
complicated.
Oh,
it
that's
just gets more
perfect.
complicated.
Yeah,
We can
that's
start
perfect.
at 6.1 if we want to.
Yeah.
6.1 is like very simple.
All right. So, is everyone able to get to the binary collection?
Yeah,
Like,
they should be on the desktop, I think.
good.
Yeah.
Ismail, you got it? Okay, cool. So we're going to start with Lab 6.1. I think drag and drop is enabled. Yeah, it is. Okay, cool. So do you guys want to start with basic static? I'm not doing basic dynamic because it'll take too much time. Okay, we'll start with that because it's really quick.
Yeah.
Um,
It's usually
So this goes back to the process we were talking about, right? So the first thing you're probably going to want to do is run it through PE View to see like the imports and the exports associated with it. So again, we're doing Lab 6.1. So PE View is the magnifying glass for those of you who are unfamiliar with it. We click that and we load Lab 6.1. You can see in hex our binary, right? And we see the familiar MZ starting our binary. We also see familiar string, this program cannot be run in DOS mode. Great, we know we've got a binary on our hands. So just not to bore you guys, we're gonna go a little faster. So we're gonna look at the import address table and we can see all of these different functions that are used within the binary. Of note, we've got when inet, so internet get connected state. That's kind of interesting. So if we were doing basic dynamic, hey, maybe we'd run Wireshark and inetsim or something along those lines, or a pat DNS. We see terminate process, get current process. So do we see get proc address and load library? So we might have some runtime linking. File type. Does anyone notice anything? Oh, that's freaking tiny. Is everyone able to run this through PE View? Great. Has anyone seen anything that I have missed? I see write file.
Set file pointer.
Set file pointer. Okay. Anything juicy? Not a terrible amount of crazy stuff in here. Okay, so we get an idea. These are the functions we're running through.
See, good old get proc address and load library.
Yeah, we got get proc and load library. So let's go over to strings. So we're going to open up the command line over here. We will navigate to chapter 6. Oh gosh. I sure love that. Okay, so there's our lab 601, and we'll do strings lab601.exe, and we'll pipe it over to text file. Because believe me, you do not want to run that on the command line. And we've got, we saw this before. Program cannot be run in DOS mode. Bunch of garbage. Okay. Some errors. So this is like compilation stuff, is my understanding. Program name unknown. Okay, so I don't think we saw this before. So that might be what's being runtime linked right here. So we've got oh, that's freaking tiny as well. Can't read it, or I would recommend you do this on your computers because it's really good to get familiar with like actually doing it, as opposed to knowing how to do it, because that's how you get better at this stuff. Get last active pop-up, get active window, message box A. Sometimes you see this in keyloggers. I kind of doubt this is a keylogger right now. It could be. See all those different functions we saw before. And we see an error message with no internet and internet connection. So that kind of leads me down the thought that maybe it does actually establish a connection, but we don't really see anything else in strings. So I'm going to skip basic dynamic because it'll take too long and go straight to IDA. So I've launched Lab 6.1 in IDA free right here. And to make it easier on yourselves, this is what I do when I load up a program is I go over to toolbars, I switch off main, and that gets rid of like some of the stuff I don't really use too often. And then I put on line prefixes within the options just so I can know exactly what memory address I'm looking at. And so it's easier when I go into advanced dynamic analysis. I know where to set the breakpoint exactly, and I can refer to that. Again, we're not doing that today, but yeah. So thankfully, and this goes back to saying why Ghidra can be better and how IDA has digressed. We dropped in main. With newer versions of IDA, that's not going to be the case. You have to find main. I'm not sure exactly why or what the history of that is exactly, but thankfully we have an older version of IDA, so it drops us straight into main. So this is what's going to be run along with other things when we actually double-click that program, right? So from this, can anyone tell me what it's doing? Or what I might look for as I'm looking at this malware? Yeah. Is that better? Does it need to be bigger? Okay.
A whole lot of extra text in mine.
Okay.
My view of that.
Yeah. So does it look like this? Thanks, John.
I mean, I see the same view you have. I just have, I don't know.
Okay, so yeah, so we're going in through here, and immediately, or almost immediately, we're going into a subroutine right here. Then we're moving what's returned into, or returned from that subroutine into this variable here. And then based off of that, we're comparing to 0, jumping somewhere, and then based off of where we jump, we either zero out EAX or we return 1. So in general, like when you're returning from a function, what's returned is usually stored into EAX, and you know that's that. So with this one, it's not super interesting, but the subroutine could be interesting, right? So the way you go into subroutines is you can either, press G and go into 401000, or you can just double click the subroutine, and that'll take you to the location. So you can see right here, this is the memory address 401000. And immediately we see an API call, internet get connected state. So when you're looking through this, hold on. Call DS internet get connected state. So this is a Windows API call, and like I mentioned before, you're passing arguments via the stack, so you push values in here. And IDA is nice enough to label or recognize that this is an API call, and I think Dr. Springall mentioned this last week. It's what is the name of recognition, like the technique of recognizing API calls? Flirt signatures. So this is a prime example of flirt signatures in action, right? So it recognizes that this is that API call, and those pushes are the arguments associated with that call. So in this case, we push 0 and 0 as well as ECX into internet get connected state. And then based off of what that does, we push the return value into var4. So what does internet get connected state do? And how do we find that information if we don't know? Google it. All right. So can anyone Google that and tell me what that does?
Retrieves the connected state of the local system.
Okay, cool. So it checks if there's internet connectivity. Most of the API calls, because it's so verbose, you can kind of figure out what it does. There are a couple scenarios where that's not the case. Get module file name is one of those where it's like, what are you talking about? So we return the connectivity of that computer to the internet, if you will, and we store that into var4, right? We're comparing it to 0. So what happens if it is 0? What does that mean for this program or the host that's running this?
You're jumping to the, you're going to jump to log to the location 401-2B, which would be the one on the right.
So how can you tell which of these directions is true versus false?
The name is location of the second one says.
So another way, and
Also the green arrow.
yeah, green arrow is usually what I go off of, but yeah, you can look at the memory address. So IDA kind of labels it, makes it a little easier. So we see, okay, if it is equal to 0, we go this way. Oh, excuse me. No, we don't. We go over here. Actually, what's the return call? What does it return? That get internet connection connected state. What is a Boolean? Okay.
It just says that under the cover over it.
Okay.
Oh.
Okay. Yeah.
Oh,
So
interesting.
if it's a 1, does that mean it's connected? Probably.
Also another
We could
great
check.
way to find this, the MSDN docs.
Yeah, so I would
Is
recommend going to
parameters
MSDN and
return
checking.
values for those functions. So
Yes. So as you're going through malware, you're gonna get familiar with MSDN. I can tell you that now. So what if it's connected? What does this function return?
I mean, I would just guess 1 because it would continue, and if you're checking for if it's equal to 0, and 0 is the one where no internet is. So
I think you're right about that.
It is, yeah, it returns true if there is internet, and it returns false if there's no connection.
All right, so we go over here, success internet connection, and then what do we do?
Move the AX to 1.
Well, there's a call here. What does this call do? A lot of scary stuff. So as you do more of this, you're going to recognize that that is printf. Usually if you're pushing like a big string, or you're printing multiple strings right before a function call, you can make some assumptions that it's probably a print statement after that. And if you go in and you see like, oh, stbuff and ftbuff, and then a big tree over here with getting string types, yeah, that's a printf. So one thing to make our lives easier is you can label these functions by pressing N as you highlight it. And you can say, okay, this is printf, and boom, call printf. So for every, that memory address is going to be the same across the entire binary. So if we ever run into a printf anywhere else, like say if we're saying it's wrong or no internet connection, we can see immediately, okay, it's calling printf. So it just makes this whole process a lot easier. You're going to find as you go through bigger and bigger binaries, this is going to be more and more important to do because you're going to run into subroutines that do like logical things, like this sets up persistence, or more granular. This deals with like registry magic, right? It sets a binary, or sets a bunch of registry values and stuff like that. So you want to make your life easier by labeling things, so as you go through, it becomes quicker and quicker. But from this, we can see if we get a connection that's successful, like I think Tyler said, we move 1 into EAX, which indicates, hey, we were successful. So, and we return that value, and if we want to go back to what we were looking at before, what called this function, we can either go to the very top, the 401000, right, and look for a cross-reference, or something easier at this point is we can press escape, and it takes us back to the call. So if I were to try to make this a little easier for myself, although we're pretty much done with this program, what might I do to this subroutine and name it? What did that subroutine do?
Got the internet connection.
Okay, check connectivity, right? Oh, it's too long. Check connectivity. So now we can see that this piece of malware is very, very basic, and it just checks the connectivity of the host that it's running on, right? And it prints it out to standard out, right? So that's that for that malware. Let's see if it gets harder.
Well, we'll say,
What's
I
up?
was gonna say you could with that just one thing like what is the main function return based on stuff.
Oh, that's true. Yeah. So let's
Just
go
like
back.
a
So
thing to deal with. It's fairly simple.
let's see. 6-1,
That's
right?
fine.
No, we're here. So like John was saying, one thing we might do is like if the main function were successful, we might look at like what's actually returned from it. Oh, there we go. So we go through, and before we saw that 1 is returned into here in EAX, we compare to that. So if it's not 0, we jump over here, which means we move 1 into EAX, and then boom, we go over here. So it looks like it returns 1 if it's successful, or if there's an internet connection. So yeah. We're going to go on to Lab 6.2, or we can go straight to Lab 6.3.
6 to you said they sort of build off each other.
Yeah,
They do build on each other.
Might be good to go. Just 'cause.
Okay, we'll go Lab 6.2. So whoops. What 2 programs am I going to use for basic static?
PEView.
Okay, what does PEView do?
And then just looking for your imported functions.
Right, so we're looking at the imported functions. Do we notice anything different here? I do.
Well, I mean, you have a lot more under when inet.dll this time.
That's true.
Last
Yeah.
time you just had get connected state. Now you have open URL, read file, open A. So that might give you some idea of what it could potentially be doing now.
Yep. So more internet imports. So let's run strings on it. Oh. Okay, so we've got a URL now. Got Internet Explorer. What is what do you guys think this does based off of what you're seeing here?
It's opening your files. So that says like the failure file.
Okay. Yeah, could be opening a file. So one thing you should be very careful about as you go through basic static is never make concrete. Don't make your assumptions here concrete, because you can only assume with basic static. But it's like John was saying before. This gives you an idea of where you can go from here. But yes, that's a really, I would say that's a really good assumption right there, or good idea. So it's probably, reading a file or opening a URL and maybe even pulling commands off of it, right? So we'll launch off of IDA. So on 6.3, I'm not going to walk through it with you guys. So I want you guys to walk through it, do this on your own machines, and then tell me what it's doing. That sound good?
For 6.2, right?
6.3.
Oh, okay.
So we'll do this one.
We're in 6.2.
And
Okay. I
then
was gonna say I don't know time-wise.
boom. Oop. All right, so beginning looks pretty similar. Go through, we get the connection, check the connection. Based off of what's returned, we can see there's different stuff that occurs based off of what we see, right? So if it's not 0, which would imply it's anything but 0, we go over here and we make an additional call that we didn't see before, right? Is that big enough? Is it too small? Okay, cool. So that subroutine's new. Other than that, if there's no connection, we're going over here and we're returning 0, right? Because we XOR EAX, which would make EAX 0, right? So the really interesting stuff's on the right. So we're going to keep going. It looks like go over here and whatever's returned is pushed into var 4, or excuse me, var 8. And then we check the value of that here. And if it's not 0, we say, hey, parse command. Otherwise, failure. So we didn't parse the command, assuming. Go over here. This looks like printf to me. It's printf. So printf. Based off of that, we parse the command and then we sleep. What does sleep do? It's the same as any programming language. If you don't know, look it up and then tell me.
How much time you got?
Well, no, like from a high level perspective, what does sleep do? Like from a, if you're running this, what is sleep doing? Once it hits this. It's sleeping. It just waits, right? So we wait, right? And then based off of that, after a wait of however many milliseconds this is, we go on. We actually return 0 in this case. But so another little trick we can do here is we can either right-click this and figure out, hey, this is decimal, 60,000 milliseconds, which is what, like 60 seconds? So it waits a minute. Or you can go and press H, which would convert it from hex to decimal or decimal to hex. We parse the command and then we wait, right? So let's go ahead and look at that subroutine and see exactly what's going on here. So based off of what we see, what two API calls are we using here?
Internet open A, internet open URL A.
Okay, so internet open A and internet open URL A, excuse me. The A is just like a convention within Windows. If you're confused, you might see EX, which means extended, which means they've made additions. There are actually Windows API calls that say EX A, I think. So welcome to Windows. There's also W. You'll see that as well, which means wide. So we push a bunch of different values here to Internet Open A. So can anyone tell me what Internet Open A does?
Is it opening Internet Explorer 7.5 PMA?
I don't know. Is it?
That sounds
MSDN,
like
trust me, the MSDN docs are amazing.
I'm not giving you a hard time for no reason. So
They're
this
very helpful.
for anyone who's done like any web stuff before, what does this kind of look like?
it says something about WinNet.
So that's kind of like a user agent, right? Kind of looks like a user agent to me, at least. Which might tell us some like versioning of the browser you're using. But we also see something that's kind of odd attached to that. We see PMA. So that's a little weird. So I'm pretty sure this gets a handle to like an internet connection or to it.
It actually just it initializes. It basically is saying this application is going to use stuff from WinINet.
Okay, so it's kind of like your SC Manager A, right? So
Yeah.
so in Windows, there's a lot of initialization that goes along with prepping for basically any like complicated task. You see it in registries, you see it in service creation, you see it in internet connections. So in this case, it looks like we return something called H-internet, and there's things called handles within Windows. We're not going to get into handles today because I don't want to. Look it up on your own time. They're important, but in this case, I'm pretty sure this is passing a user agent or saying it's passing a user agent, and it's getting a handle to something that's later used for internet connectivity, right? So what is Internet Open URL, and why should I care?
It opens a resource specified by a complete FTP or HTTP URL.
Okay, so it takes a URL. In this case, and here's another trick. You see this push offset SZ URL, right? That's our string. That's our URL. And again, I just kind of made it simple for us. But you can hover over the variable, or whatever you want to call it here. It's actually it's a memory address if you really get down to it. And this tells us it's going to http www blah 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 cd.htm. So that's again, we saw this in strings, right? So this is one thing that kind of popped out to us and we knew to look for, right? So this is that resource that we're pulling from, and based off of that we get a handle to a file here, right? So what's returned from Internet Open URL A.
Returns a valid handle to the URL if the connection is successfully established or null connection fails.
Cool. So yeah, we get a handle here, and then boom. If we do a comparison, if it's 0, null in this case, we would say, hey, that something's wrong. We go on this path. By the way, you can double click the arrows and it'll take you to to what that jump would go to. And you can see we see an error, 2.1 failed to open URL. And we internet close handle, so we're closing that handle that we initially created. Otherwise, we're going in and we do boom. We see, hey, we've got a valid handle. We want to read from that handle now. So we've pulled from that URL or that resource online, and we create a buffer here. We get a handle to the file that we had gotten, and then we read into that buffer as far as I can tell. So yeah, here's where it gets a little more complicated. So that aside, so we've now read into a buffer. We can see here. We'll gloss over that so you guys can work on the lab 3 really quick after this. And we do some comparisons here. I'll leave you guys to figure what that is doing. But it looks like it's trying to read from the buffer 1 byte at a time, and it's looking for specific values. So one way we can check for what it's looking for, and you'll see this in CrackMe's a lot, is we can actually convert this over to its ASCII equivalent by right-clicking it or hovering over it and pressing R. So we see, hey, if we go in here and it's a less than, we want to continue, and the first character of that file is a less than. If the next character is a shebang, or not a shebang, sorry, an exclamation point, we continue. Otherwise, we exit, right? If the next character is, what's the next character? Is anyone following along? A minus or dash? Okay, so a dash. And then what about the next character? Same thing. So what does that look like to you guys? Are any of you familiar with HTML? An HTML comment, right? So it's pulling this this file, or it's pulling a resource from the internet, and then it's checking for a comment. It's kind of weird. So what happens if it's successful? It goes right here, right? No, it doesn't. It goes over here.
Yeah, it goes there. That's
So it gets a value right here, jump not 0. Okay. We got our printf, and then it looks like it's trying to get a command from this. So it's looking for a binary. It's looking for, well, not a binary. It's looking for something it pulls from the internet that looks for a specific HTML, comment, and then it pulls a value from there. And then guess what? That appears to be a command. So if we go back to the call, so this AL value appears to be a command. So whatever's in var8 should be a command. So we might do like command, right? And this is get command. So we go through here, and that appears to do the same thing, right? So look at lab for the next 10 minutes. Look at lab 6.3 and tell me what it does. It's going to be pretty similar. If you don't get through it, that's okay.
also, if you get stuck somewhere, because there's something in lab 3 that I don't think we really talked about, and I don't know if you would intuitively know what it is. My computer is not working. Please fix it.
You know, I right here fix this. Probably this is.
Everyone figure it out? Anyone having trouble? Need help? Okay. So can someone walk me through the first part of this? What is this block doing right here?
It's checking your internet connection.
Okay, so goes in here. It checks for internet connection. Okay. All right. So if it has an internet connection, what's it doing? Goes over here, right?
Yeah, it jumps over there.
What is this doing?
It's a command.
Okay. It's command. Okay. So if it gets a command, it goes over here. And I'm guessing this is printf, right? All right. So this is new, right?
Yes.
Okay. What does this do? So anyone figured this out yet? Sort of, kind of. Let's hear what you figured out, or you think you figured out.
Well, looking at the streams, you could see part of it's trying to do registry editing. Has something to do with reading, writing files.
Okay. So
What I
yeah.
couldn't figure out was I understood the end goal. I didn't understand how we got there, so I was spending all the time looking through that. Like I didn't understand some of the arguments get passed into this part, which apparently is very important for deciding which way to go.
Okay. Yeah. So like you said, you've got registry stuff over here. You've got copying of files, creating of directories. Looks like deleting file. Okay. Got a sleep, and then you've got like looks like something that says not a valid command provided. So sounds like options, right? Perhaps. So where is it deciding on options? Like where to? Can you give me like a memory address? How would we find that?
00C.
Zero.
Oh, well, I guess.
Let me see.
Or that. I don't
This-
know why
This one?
that one. I don't know why mine all say.
Okay. So this one, right?
That looks like a switch statement.
The switch
Yeah.
statement? Yeah. So like, all right. Before we get to like the structure of that, it looks like it's all contingent on this var 8, right? Because that var 8 is passing to EDX, and EDX is then determining like something right here, right? Maybe I'll blow it up here. So how do we land on var 8? And you can highlight it here. You can see, hey, we go over here, we compare it to 4, and based off of whether it's 4 or not, we take one of two paths, right? But before that, we see, hey, looks like we're subtracting it by a value, right? So if we wanted to look at that value, we might go and do R, and we see it's subtracting by A, right? So maybe that's the command we saw before, and then it's subtracting by A to keep it within a certain bound, or to get which case it's going off of, right? So then we see, okay, so based off of that, we're passing it a value, and we're landing on some number right here, pushing it into var 8, and then we get to whatever the heck this is. So does anyone have any ideas on like what this might be, or how we might figure out what this is? Like there's a term in assembly for what this is. And and there's a C construct that maps to this typically. Actually, two really, but so this is called a jump table. So we've got an offset here with our 0 or our EDX, so that case we got before, and then we're multiplying by 4. So that's the offset times 4. So we're going into this memory address and we're returning whatever that value is here. So we can see that within this, we're returning a memory address, and that memory address is associated with whatever's in here. So we're going to a specific like area off of that, and that's called the jump table. So yeah, so we get our case, and then based off of the value we passed in or the command, we're going to a specific like chunk of code, right? So in one scenario, when EDX is 0, I'm fairly certain, we go over here, right? And it looks like we're creating a directory temp, right? Another scenario, we're going in and we are, copying a file into cc.exe? I'm not sure. I'd have to look at what's being passed. This file into this, or the other way around?
No, yeah, like the file the exe you're in, you're copying it to temp.cc.exe.
Okay. And then with this one, copying it to a new file. Okay. And then for this one, we're deleting that c.exe, right? And then, like you were saying before, I think your name's Tom. This is some registry stuff, right? So with this, we see that we have some long registry key called software Microsoft Windows current version /run. So that's a pretty important and well-known thing. So if you were to look this up, what do you think this block of code is doing, and why are they doing it? I would Google that string right there and see what happens.
Could it be running the program?
Potentially. I think it's a little more than that, but
Could it be running the program at a specific during a specific time at?
I don't know. What? So this is called this is really persistence. So it's setting up persistence with this registry key. So every time whatever user logs in or starts the system, it's going to kick off the binary that's there. This is persistence technique right here. And it looks like that's the name of what is it referred to as a subkey, I think is what they call it in Windows. But like within this malware subkey is going to point to this binary, which is going to kick off every time we log in as that user. So pretty suspicious.
The use of a value, or so subkey with a value that then has data is never set well with me.
Windows, man. But yeah, so that's what that does. And then otherwise we have a sleep command, which you see this a lot in like C2s and stuff like that. So yeah, sleep, and then if not, hey, we're it's not a valid command. So yep, that's what this binary does. You got it, man. So yeah, there are additional labs. These are all available online. I would encourage, like, if you enjoy this, go poke at them. Use a VM, but go poke at them. Have fun, and well, I think next week is the wrap up, but we might be doing game hacking. Oh
Yeah, next
shoot,
week's
the week
Thanksgiving break.
after next. Sorry. we're doing a wrap up and then like game hacking. So some of the stuff that we've shown here kind of applies. The same mindset applies to game hacking. But yeah, that's all.